Hi, I'm Kyle Bates-Green, subject matter expert at Edmonds Community College for the TEAM grant, here to talk to you about the additive manufacturing process chain from brainstorming to final product. Today we'll mostly be talking about fused deposition modeling, but we'll discuss a few other ways in which we can 3D print things as well. The FDM workflow looks just like the engineering design process in many other places. So for fused deposition modeling, we'll start at design, produce some geometry files, then slice them into layers, which will produce tool paths for our machines. Inspect those and decide whether we need to go back to some previous step in the process. Generate G-code, which is the actual instructions, just like on a CNC machine, for where the tool path, for where the tool head is going to be at any given time. Print that object, evaluate how it achieves our goals, and then go back to redesign again. So when we're designing for three-dimensional printing, we generally use CAD, computer-aided drafting or design. We can produce geometry for our additive manufacturing processes in a number of ways. That can be drafting, modeling, sculpting, also scanning in or generating geometry using either 3D scanners that produce some point cloud or facets, or using mathematical equations to generate those shapes and then passing them to the next step independent of CAD. In the example here, you can see that we have a simple manifold part that's just dimensioned. We made this one in SketchUp, but there are many other programs that you can make it in. The next step in the additive manufacturing design process is that we need to turn our geometry into an STL file. STL is currently the standard for additive manufacturing, may not always be, but it's usually used as something of a backronym which describes its behavior. Standard triangle language or standard tessellation language are a couple of examples, but we would call it stereolithography frequently. As you can see in the example here, we've taken that geometry and we've turned it into triangular facets. These triangular facets are able to fully describe the surface of our manifold object without any missing parts, but we can see that the algorithm we've used to generate this STL file, which we've brought back into our CAD space so you can see where the triangles are positioned, may not make the optimal decisions that we would have made if we were drawing the triangles. Some of them will be very long, very thin, skinny facets and may not have the proportions that we would have chosen for ourselves. Also, STL files are in arbitrary units, which is one of their problems. It's not okay to just give your technician or whoever's operating your additive manufacturing machine an STL file, because in an STL file, 1 is a distance of 1, not necessarily 1 millimeter or 1 inch or some other calibrated unit, but rather we must pass other information along with this. And it's not just the scale units, but also information about the operating temperatures and what materials can be used. What we see here in our example is some of the data inside our STL file. So we're going to need at least 12 data points for every triangle that exists in our STL. Slicing software, frequently just referred to as the slicer, though there is one slicer which is called slicer and others which have many other names, takes our STL file and turns it into layers. In the example of the machine we have here today, a simple consumer-grade FDM machine, those layers are by default going to be about 1/5 of a millimeter each. However, that's not always the case. The slicing software needs to deal with a number of settings, including build plate orientation, which way your geometry is oriented on the build plate, which faces down, and how it's rotated around that z-axis. It also has to deal with the scale, because once again we can change the scale in our slicer software, and we can also decide what units it's imported in as. And it needs to deal with all these other settings that aren't contained in our STL files, such as the temperatures of the extruder and the build plate, the rates at which the extruder travels when it's extruding and not extruding, the rate at which it extrudes while it is extruding and traveling, the thickness of those layers, the resolution of the movements which it makes, a number of building methods such as the algorithm that we use to decide the infill of a shape, and the density at which we make that infill, the density, the thickness of the shells, the number of shells on the outside layers and the floor and roof of it. automatic algorithmic generation of rafts and other types of supports, and a number of other more complex settings that we can deal with, such as handling the atmosphere temperature inside the printer, which we can't do with a consumer grade machine quite like this one, but with some larger commercial machines you may see. So the next thing we look at are the tool paths inside our slicer. This is still inside our slicer software generally, but it's a visualization of where the tool tip, the tip of our extruder in this case, is going to be at any given time inside of our print. We also know that our layers are going to be fused on top of each other one layer at a time. So we can see that visualization when we look at our tool paths as a whole. We can also use this to predict any errors that may happen that our slicer doesn't predict, or that will happen as a result of some setting that we have changed. Perhaps we've prevented it from generating supports in a particular place, and we need to see how that's going to happen in our final result. Here we see an example of some of the G-code that's generated by our slicer software. The G-code is built on top of M-code, which basically just means it has a few extra instructions that CNC machines would not normally need, such as the tool tip temperature or the build plate temperature. In the text blocks you see here, you have some commands built into G-code, such as traveling to different locations at different speeds. These commands can be given in a number of ways, and we took this example off reprap.org right here. It's essentially the same as CNC commands, once again, but has some extra commands built on top of it. And these are simply the commands that are passed to our standard CNC frame right here, whereas if we were using a cylindrical coordinates, for example, then those commands would look a little bit different. So there are a number of advantages we have with additive manufacturing over other methods that are going to change our decisions for how we're going to prototype and what decisions we make even at the brainstorming step in order to turn those into a finished product or a finished prototype for turning into a mass production process later. Additive manufacturing allows us especially to make very complex geometries. We're going to take a look at a few examples of that, but the most important things to keep in mind are that we can leave internal spaces where we decide to do so, especially with fused deposition modeling. With other methods, we may trap our excess material or uncured material like resin or powder, in the case of powder metal printing, inside of those empty spaces, but with fused deposition modeling, we're only trapping air inside. We can also produce trabecular structures, things that would be uniquely difficult for subtractive manufacturing to make, and perhaps impossible for formative manufacturing to make. We can also blend materials in a way that we can't with other manufacturing techniques. And we also, because we can blend materials, especially with more advanced techniques like droplet printing, we can blend materials together at the level where we get a gradient between different material properties in different locations. One of the biggest advantages of additive manufacturing production is in short-run production, especially in the case of prototyping, which is sort of the ultimate short-run production. We want to produce one piece, maybe a handful, that do exactly what we need to show for our final product, but we definitely don't want to set up an entire production process for that. Additive manufacturing gives us really perfect advantages for that because we have a very short time to the first product. We don't need to produce molds. The amount of tooling we need to use for this machine is very small. There's almost no tooling changeover. We may be generating our own supports in the printing process, of course. And it also gives us the ability to mass customize. Because we can alter our shape with no tooling changeover, then we can take one prototype and make many versions of it very quickly without generating separate molds and without changing very much about our tool paths at all. Since for additive manufacturing, it's often time that is the limiting factor rather than, say, the number of technicians working on it, the machine may be able to continue on its own, but can only extrude so much material per time. Then having massively parallel systems to produce lots of things at once is usually a bigger advantage than, for example, producing parts in series, whereas an injection molder may make many parts in one mold. Additive manufacturing frequently more effectively makes one part at a time. One of the most important advantages that additive manufacturing has is its ability to change the supply chain. It's not that it is superior to other methods of production, but rather that it can fill niches that the others can't. So if our even just a couple $100 3D printer, like the one we have here on the table, can produce very complex parts with very little in terms of requirements for tooling or technician skill, then this changes the way in which we can distribute production and material and finished products separately from each other. So if we want to have a catalog of updatable electronic designs stored with this machine, then we can manufacture them on site rather than storing finished product on site and taking up a lot of inventory space for parts that may or may not be used, statistically speaking. We can think of cases where that makes additive manufacturing clearly the best solution to our problem. For example, if we want to take a large amount of replacement parts to Mars or to some other remote location, then it may be more effective for us to take raw material and a small manufacturing plant, like a 3D printer, rather than taking a large catalog of parts. So in terms of changing our process from brainstorming to deciding how we're going to make our final product, additive manufacturing also gives us the chance to consider whether it is a good part for additive manufacturing, whether storing it is costly versus producing it on site, whether it is a critical part that may be in low demand, so we don't know how often it's going to be used or how much it's going to be customized when we do produce it. And we also have to ask the question whether it's more efficient for us to store that raw material, which may change over time, which may age. And we also need to decide whether bringing raw material to the site is difficult or whether something may be present already. So in order to see the advantages and disadvantages of our particular fuse deposition modeling setup here, let's take a look at the hardware. So our extruder here essentially acts as an advanced hot glue gun. It runs at generally a much higher temperature, and it's pulling in material using a motor here that turns a feeder gear, so we have a control for the rate. However, other than that, it's not really that much different than a hot glue gun or some other simple extruder. The extruder tip underneath can be made of a number of different materials. Brass is generally a cheap and effective option for that. However, if you want a more durable tip, titanium carbide would be a good choice. We have here a fan which is not to be overlooked. It's not just for helping the extruder assembly get down to temperature afterwards, but rather, most importantly, this fan is cooling the plastic as it comes out. We're constantly making a balance between the high temperature that we want it to come out at in order for the plastic, in this case, to fuse to the previous layer, and the low temperature that we want it to reach quickly so that it freezes in place instead of changing the dimensions that we place it in. We also have another case fan here, cooling vanes for the extruder assembly, and then down here we have a build plate. Also not to be underestimated, the chemical properties and surface properties of this build plate are very important. This one is heated so that we can maintain a sort of atmosphere temperature just above the plate, but also help adhere our material to it. And then our material itself is fed in through the top of the extruder. This we would call the filament, and in this case we're using polylactic acid, a thermoplast, which comes off of what we generally just call the spool up here. On the sides we have our CNC operation. Once again, this could be Cartesian coordinates like you see right here. There are a number of other interesting and novel solutions out there, but ours is just traveling up and down on a couple of stepper motors, whereas our build plate moves in our y-axis here. And then finally we have some sort of control mechanism. This may be very simple, it may be very complex. In this case what we have is essentially a microcontroller. So if we think of our FDM machines as basically advanced hot glue guns here, then we can start to think about some of the challenges they have, the limitations that that hardware has. One would be that we can't extrude melted plastic and expect it to float in the air. So we have some limiting overhang angle, an amount by which, an angle at which, we can no longer support a layer above a previous layer. There are many ways to deal with that, such as cooling faster or by building supports underneath it. We also have another set of errors, retraction and stringing errors, which we'll take a look at in just a moment, where the extruder is not able to cease extruding material when it moves across an empty gap that by tool paths should not have any plastic in it. So we get a thin amount of material instead there, instead of an empty space. We're constantly making a decision between speed versus resolution as well. We want to minimize the amount of time it takes to print our object, but we also want to keep our dimensions as accurate as possible. And the faster one of these machines runs, the more likely it is to deviate from that ideal tool path, especially since we may be setting up some amount of oscillation in our frame. So a more damped or a more rigid frame will allow us to run at a higher speed, but once again, that'll increase the cost of the machine and will require some other changes as well. We also have the limitation of build plate adhesion. If we make a very broad, flat object, then it's going to have a strong tendency to curl up at the edges, simply because of our coefficient of thermal expansion, of course. But if our material has a sufficiently low glass transition temperature, then most of its shrinking will happen before it stiffens. So if we have a high glass transition temperature, then it will stiffen and then shrink, meaning that any new layers placed on top will tend to stiffen up, apply pressure to the layers below them, and then shrink, causing more curling. And also, of course, we have a large number of limitations simply based on the materials that we can use. Here we have a thermoplast, polylactic acid, running into our machine. There are a lot of other common plastics, such as bridge nylons or acrylonitrile butadiene styrene, ABS. We could use HIPS as well, high-impact polystyrene, which has the advantage of chemically being degradable in places where other plastics wouldn't be. So we could use that as frangibles, right, supports, things like that on our prints. But all of those share that one property, that they are thermoplasts. So with this type of machine, we have to be able to melt a material, flow it into place, and then solidify it in place. So there are a lot of materials we couldn't use. We can solve some of those problems by putting fills, by using thermoplast fills. We could embed particles in this plastic. Of course, then we would be adding something else to the mix. We'd have to change some of our heating properties. We might have to make our nozzle more durable as a result, especially if we're going to put glass or carbon fibers into our plastic. And we could modify this machine to extrude other things, such as chocolate, or to extrude sugar by suspending it in isopropyl alcohol, dissolving that solvent quickly as it extrudes a thick supersaturated slurry, and then as a result crystallizing that material in place. We could modify this into a pump where it puts some aqueous solution of human cartilage or human collagen into place in order to build a structure slowly, a scaffold for cells or an implant itself. There are lots of solutions we could come up with, even to pump concrete slurry into place. Those are all options for fused deposition modeling. However, in order to print things like ceramics or metals, we would have to extrude those into place and then bake them afterwards. So generally, for materials like that may be too high temperature or may not be able to travel in a liquid form to our build plate here, we might move on to some other technology, such as plasma deposition or laser sintering or electron beam sintering, or curing in the case of resins and thermosets. So in order to maximize your effectiveness in the design cycle using fused deposition modeling, you're going to need to optimize your designs for the speed at which you print them, perhaps the print orientation in order to get the layers in the direction that you want them. You're going to need to optimize your design for the material that you know you want to use, and you also may need to optimize it to compensate for any supports you need to add. So if you know that your geometry that you need for your product is going to have overhangs no matter what print orientation you place it in, you need to also then optimize what types of supports it's going to use, how they're going to be detached, that sort of thing. So you're going to balance these different factors against each other in a different way than you would for a different manufacturing process. So the decisions you're going to make to optimize those for FDM or any other additive manufacturing process are going to be very different than the decisions you would make to optimize for those factors or others if you were injection molding a part or machining a part. So we mentioned a number of materials that we could use for additive manufacturing. For fused deposition modeling, of course, those thermoplasts, thermoplast fills, and a number of different slurries that we could modify our machine to work with. However, if we want to work with SLA printing, then we're going to be using ultraviolet curable thermosets. If we want to work with powder metal fusion, which can be done in a number of different ways, sintering, etc., then the materials we're going to work with are generally going to be aluminum, titanium alloys, stainless steel, or brasses. And if we work with a more advanced droplet spray machine, then we may be able to blend a lot of different material properties all at once. That machine may be able to cure and solidify materials in a number of different ways and also blend them much more easily than we can with a machine like this, even if it had multiple nozzles. So let's take a look at some of the advantages we have with FDM. We have here two objects made off the same machine, off the same spool of material, to the same dimensions. However, there's something different inside of them. These were the same in their CAD program, but once we brought them into the slicer, we produced them with two different settings. This requires very, very little out of the technician or even the designer working to produce these parts. However, we have different properties as a result. Because we have generated a different amount of infill inside of these parts, we can see that one is less dense than the other significantly. So we have one here that is about 8% internal infill, and we have one here that's about 32% internal infill. And not only is their density different from each other, so of course things like their buoyancy are going to be different, but furthermore, if I place this piece into three-point bending, I can feel manually that our denser piece is much stiffer. This allows us to make decisions about the structural properties of what we print that are different than just the surface geometry, that are not determined by the bulk properties of our material. So I could have a part here, for example, at a low density, that produces less stress shielding for the other materials that is bonded to in its final application. A great example of that would be if we are using titanium femoral hip stems, we may want to, with that prosthetic implant, we may want to have our component be as flexible as possible, even if the material isn't as flexible as we want it to be. So we want that low modulus so that the bone in the patient that's interacting with our titanium 3D printed part doesn't stop growing, because that bone continues to experience stress, and the titanium part, which is now more flexible because of its low infill and therefore its low modulus, it remains flexible, the bone continues to grow, and the patient doesn't suffer from osteoporosis, for example. We have another couple examples of what you can do with infill. So right here you can see that we can use different algorithms for producing that infill. Right here we have a design that's just different layers. Each rectilinear layer here is produced in one direction. So we have alternating layers in each direction, which end up fused together, but that allows us to optimize for print speed. However, here we've optimized for print strength by producing this hexagonal honeycomb infill, which is much stronger but takes much longer to print. Frequently, this is going to be sufficient for us, especially if I'm doing a quick draft prototype. However, this may be what I'm looking for. Of course, these are both repeated two-dimensional designs. We could take a more advanced slicer, perhaps, and use a three-dimensional infill, or even replace our surface shell with some repeated three-dimensional shape, which would allow us to have perhaps more isotropic properties, or anisotropic properties. We have a couple examples here of shapes that are very easy for additive manufacturing to produce. We can see why that would be once we start to think about how it makes our shapes. So every time the tip has to pick up, stop extruding, or change temperature, then that adds extra time to our print. However, even though this shape right here, this kind of folded shape, would be extremely difficult for us to machine out, or perhaps nearly impossible for us to injection mold, it's extremely easy for additive manufacturing to produce simply by extruding each layer continuously and then moving up one layer. The tip never has to pick up. It simply changes between layers. It never has to move across empty space. It essentially never has to stop moving. And that also means that by never stopping moving, we never really get any change in our flow properties. We have another example of that here, where we just have a thicker wall. And we can see that this would be pretty difficult to make, especially with that small neck right there into an interior chamber. However, we can see that we made our raft on the ground right there, and then made the bottom continuously. Even if that doesn't come out perfectly every time on the type of machine we have right here, it's a great example of something we can make very easily on one of these machines that would be very difficult to make by another process. As long as we're talking about shapes that are difficult for non-additive manufacturing to make, we have another great example right here. These are pretty precise models of a turbofan engine's internal combustion blades. So the real pieces of these are nickel titanium superalloy that are directionally solidified crystal from its melt pool with a very complex internal geometry, which we can see inside of our translucent shape right here. In our opaque shape, we can see the pores on the surface that allow fluid to flow into those chambers inside right there. Making these on a couple $100, pretty low-cost additive manufacturing machine was very easy to do, even if designing them took a lot of work. However, producing these from their real material in that directionally solidified melt pool is a multi-million-dollar process. This is another example of something that's difficult for non-additive manufacturing to make, and I like to refer to it as mid-processing. So in order to get these inside of there, our coins inside of our objects right here, all we had to do was drop them in before the manufacturing was produced, since we're building up one layer at a time. Doing this with injection molding would require us to make a mold that's partially dissolvable and contains these objects, and then we of course would need to destroy the mold or dissolve the mold because it would be trapped inside of all of those chambers right there. Machining it out would require us to start with a block of solid material, cut it, insert pieces, and then fuse it back together. However, because our additive manufacturing is a continuous fusing process, I may be able to see the layers right there, though with a more advanced machine I wouldn't be able to necessarily. But it's trivial for me, at the cost of a couple dollars or a few cents, to produce a part like this that helps us think about some of the properties that additive manufacturing has that others don't. These also give us an opportunity to look at one of the types of print failures we can have. Though these parts look pretty good, I can see that underneath any of these curves in our print orientation, this direction was up, I can see what we would call an overhang error. And we can see that on our large penny cube here as well. Small little tabs of plastic hanging down because that melted plastic did not solidify in time to stay in the shape that our design dictated that it would be. We also have an example here of our retraction error. So when we try to print our shape faster than the extruder can successfully fully cease extrusion and move across empty space without extruding, we end up with small threads like this. So this is a filament retraction error. Looks like that. It can be cleaned up, of course, in a number of ways, though we want to minimize the amount of operator time we have dealing with any of these shapes, because that's one of the advantages of additive manufacturing. But these can be cleaned up in a number of ways, such as with a heat gun or with any sort of deburring mechanism. Here we have an object which requires us to print in a specific build orientation. At first, taking a look at this object, we might think that we want to print with our build plate on this large flat face right there. However, once we look inside, the AM technician will discover that this needs to be printed upwards in this direction while closed in order to be produced successfully, because all of these moving parts need to be printed without touching each other and therefore without relying on each other for support. So all of these components, this face, this face, this face, and this face, and these two faces, will all touch the ground when printed in that orientation. If we printed it with one of these faces down, however, we would require a network of supports inside it to support all of those moving parts that aren't supposed to touch each other in order for it to come off the build plate moving, which would really defeat the purpose of producing this object. And additive manufacturing gives us a number of other advantages in terms of producing those moving parts. And this really helps us make a lot of design decisions about how we are going to make something in the first place. If we know we can produce these kind of moving parts in single prints on a low-cost machine, then it changes what we can do in our brainstorming step. It changes what we can do in our design step, and it changes the kind of challenges we can address with our production process right here. So here we have some cylindrical bearings on a bushing. Here we have a planetary gear. All of these produced in their own single prints. We have a ball bearing right here, which does show some print flaws. We can see a lot of these bearings were not 100% produced correctly, and some of them have some damage from being broken away from their supports. And yet, we can produce this on a very low-cost machine with almost no user interaction with it while it's running. And once again, we can produce very complex shapes that we can't produce really with any other process. We may be able to produce these shapes by making metal objects and then crimping them together. It's hard to imagine how we would produce it at all without additive manufacturing. We also can produce some mixed material parts. So this part we designed simply to be printed on a 2-extruder machine so that we have our stiff PLA material, and then in the center we have our polyurethane blend as well, which gives us some elastomeric properties. Not just flexible by being thin, but rather some actual elastomeric properties. And for the inventor or the designer, the ability to produce this shape at a low cost presents some very unique opportunities. You may have already seen prosthetic joints being produced, prosthetic hands being produced by individuals with 3D printers. And just adding a second extruder allows us to combine some different materials in one and make these interior parts. We could even make custom gaskets or make this hinge fully inside of a part where it would be very difficult to manufacture it. Additive manufacturing, once again, because it can leave interior spaces wherever we want, not just in terms of infill, but in terms of the structure, the shell structure itself right here, also lets us reduce mass on objects. So here we have a pretty simple kind of airfoil shape. And this is designed by a human. However, if you look up genetic algorithms or computer AI, iterative design, topology optimization, then you may find shapes like this that are even more complex and look a lot more organic as a result. Additive manufacturing is pretty much required in order to produce those parts because otherwise we can't leave that hollow space where we want with traditional manufacturing techniques. When we're thinking about the changes to the supply chain, we have here a simple object that is made to fit into a groove and fit into a well. This is a cap that we made just by iterating a few different versions, copying an injection molded part, and resulted in a lighter weight piece at the end that can be 3D printed rather than ordered and shipped to the end user. And right here we have a part that you may recognize, frequently referred to as uplink.stl. This was a part printed on the International Space Station in the Destiny module where they have a 3D printer. And this is a ratchet. So I can turn it in one direction, but it gets trapped in the opposite direction. And this was made simply on our printers right here. However, the important part about this object is that it did not have to be brought onto the International Space Station, but rather the design could be transmitted there and it could be printed in place. Obviously, this allows you to separate the production expertise from the production itself. We have here an example of a piece that we've broken off of its raft. This raft is one of the types of supports that we can produce in order to minimize the amount of warping at those corners of a shape like this. So since it has to stick down onto the build plate in order to successfully build other layers on top of it, we need to adhere those as well as possible and also try to resist the natural tendency for those corners to peel up as the layers above them attach and those layers then shrink in place. So the raft is one of the ways we solve that problem. And the raft begins with some high surface area threads basically placed down, these layers, these broad threads right there. Whereas then the high resolution layers can occur inside the shape itself. And of course, this is also a great example of a shape that's flexible because of its geometry, not because of its material. It's also important for us to be able to minimize errors by producing those supports. So here we have a raft produced with supports on top of it in order to hold up our figurine right here, our T-Rex with beefy arms. And you'll notice, looking at this shape, that no matter what print orientation we choose, it will still need supports underneath it. So it's up to us as designers or technicians to decide which surfaces will best be cleaned of supports or how to minimize print time by putting it in an orientation where there are as few supports as possible rather than putting the supports where they will be most easily cleaned up or most easily hidden. Or it may be up to us to optimize for some other property, such as minimizing the amount of material it takes as a whole to produce this part. We have here another set of examples of the kind of errors we have to deal with when we're choosing what settings and what properties we want to optimize for in our printing. Underneath these edges, you can see those overhang errors we talked about before. And underneath this edge, you see what's called a bridging error. This is very similar to an overhang error, but you can see these this layer is stretched between two support posts, two supported regions, and yet it's still sagged down even though it was under tension. So in this case, we may need supports in order to solve that problem, whereas in this case, changing the rate and temperature of our extrusion may solve the problem instead. Here's another example of one of the complex things that we can do. So this sort of chainmail material right here was printed all as a single piece and needed some amount of work to get it to adhere to the build plate correctly so that none of any of these individual surfaces on the starting layer came off and disrupted the rest of the print. However, we have some unique properties here. This is a logical extension of some of the other parts that we've seen where we can make overlapping parts or interlinking parts, no problem. However, it has some properties we haven't thought about before. It moves something like a fabric. Of course, we could think of it as chainmail, but as we make this sort of object finer and at a higher resolution with smaller links, then it'll behave more and more like fabric. However, unlike the maybe loom woven fabrics that you have, cutting one of these links only breaks one link, as opposed to creating a run or unraveling an entire patch, and certainly won't unravel the entire material like a crocheted fabric would. Additive manufacturing, especially the very accessible technology fused deposition modeling, also gives us the opportunity to shorten that whole production cycle, the rate we can get our idea to market. This is a great example of this. This is an example, this is an object that I saw online. Somebody produced this shape, came up with this shape, showed it off, this optical illusion that it produces, where from one direction the tubes look fairly angular, and from the other direction they look fairly round, simply by virtue of its topology of this top surface right here. However, this went from idea to production for someone in some very short amount of time. And it went from their example to me being able to produce this in our makerspace in less than 24 hours. That's a lot faster than you would normally be able to take a product from prototype to putting it into a consumer's hands. And in this case, they put the design out for free. However, of course, you could charge for the design or charge per print if you have a sufficient platform for delivering data in that way. So we just saw a lot of things that work well in our FDM workflow and also some limitations as well. But those should give you some ideas of ways in which we modify our initial concept stage all the way from brainstorming to the final product. Cool. And then slide 31. So that should be the whole thing. I don't know if you guys had any stuff that was